So we finished up talking about proton NMR last week. We got into carbon very briefly, so we're going to talk about carbon NMR to start things off today. When you're looking at the carbon, as we said last time, the carbon 12 is a much more abundant isotope. The vast majority of carbon atoms have a mass of 12, 6 protons, 6 neutrons, but those are not seen in NMR. So that's why we said you need a significant amount of sample so that you've got lots and lots of molecules. That way there's a decent chance that each carbon in the structure will be a carbon-13 and one or another of the molecules that are present, and that will occur often enough to create enough signal. So we need a significant amount of sample to create enough signal to be able to see these peaks. And when we look at the peaks, we typically see a carbon, the signal for the carbon will be smaller as well if there are no hydrogens attached. So if it's only bonded to carbons or oxygens or some other element, and there are no hydrogens bonded there, that carbon-13, when a carbon-13 takes the position in the structure that doesn't have any hydrogens attached to it, it's going to be a weak signal. So when you're looking at your carbon NMRs for your unknowns in Lab 7, those weaker signals usually indicate a carbon with no hydrogens. And we're going to talk about DEPT today. The DEPT NMR will allow you to see how many hydrogens are on a carbon. So if you have a carbon with no hydrogens, it won't appear in the DEPT. So if it appears in your C13 spectra but not in the DEPT, especially if it's a weak signal in the C13 spectra, that is a good indication that that carbon doesn't have any hydrogens attached to it. In carbon NMR, we use the same standard, the TMS. That's a tetramethylsilane, so it has a silicon atom with 4 methyl groups on it. And we didn't say much about this last time, but the silicon atom has a lower electronegativity than carbon. So silicon allows carbons to pull electrons away from it pretty strongly. And so those carbons all take on a little bit of a partial negative. And the hydrogens that are attached as well are able to pull a little bit more electron density than they normally would. And so they're a little bit more shielded with electron density as well. So that's why the TMS in the proton NMR is set to 0. There aren't many hydrogens. They're going to be more shielded than this. When silicon with its low electronegativity allows the electron density to be pulled away and it focuses around the carbon and the hydrogen, that electron density weakens the degree to which the magnetic field affects the hydrogen, so a smaller amount of energy will be the energy difference between its alignment with or against the magnetic field, and that small amount of energy is set to 0. So this is our standard. We set that to 0 in the proton NMR, and we set it to 0 in the carbon NMR. And so that's usually already mixed in with chloroform D. So if you're using chlorinated or the chloroform D deuterated solvent, it would usually have TMS already in there. And so when you see the peak, all 4 carbons have the same equivalent environment. So it should be one signal for all 4 carbons. You set that signal to 0, and then wherever the other peaks appear relative to that, that gives us information about the number of carbon signals and what their environments are like, because depending on where they end up on this scale from 0 to 220, that gives us information about how de-shielded they are and what the environments are like for those carbons, as we're going to see moving through this section. Just like in the proton NMR, if 2 carbons have the same environment and they're equivalent, they'll give a signal in the exact same spot. So we won't necessarily see a signal for every single carbon in the structure, but we will see a signal for every carbon that is unique. Every carbon that has a unique environment will give a signal, and any other carbon that's equivalent to that will give the same signal. So we're going to look at some structures today as well and try to make sure we understand how to predict how many signals we'll see in those NMR. If there's some symmetry in the structure and carbons have the exact same electronic environment, then they are equivalent and they will give the exact same signal. So one difference here between carbon and proton, as we said last time, the proton NMR signals might be overlapping. So if I imagine a structure like this, imagine some long chain structure here, the carbon that's directly attached to the oxygen is going to be very much de-shielded by its electronegativity, and the protons as well, because the carbon takes on a partial positive, it attracts electrons and creates a partial positive here. And when the electron density gets pulled away from those hydrogens, they're de-shielded. These two hydrogens here we would expect to give a signal in the proton NMR probably around 4 ppm. Right, so we start with the 1.2, we add a 2.5 or 3 to that due to the proximity of the oxygen, we get something around 4 ppm. The effect of that de-shielding of the oxygen really plays into the shift of the protons a lot that are right there. Once we get 2, 3, 4 atoms away, especially more than 2 atoms away, there's not much of a difference. So these two protons and these two protons and these two here, they're not technically exactly equivalent because they're all a little bit different distance from the oxygen, but their environments are so similar that their signals are going to be almost in the same spot. And if I have this one split by 2 on one side and 2 on the other side, that might give a triplet of triplets because each would be splitting that signal into a triplet. This one might give a triplet of triplets. So I'm going to get a lot of splitting and a lot of signals all in the same area. So when I look at what that peak looks like around 1 ppm or 1.2, where I expect to see those signals, it's going to be crazy. I mean, it's going to be lots of splitting and it's going to be overlapping all these signals together. So we like to see the splitting patterns with the proton NMR because a lot of times we can tell information about the structure, right? We know if it's a triplet or if it's a quartet, that gives us information about how many hydrogens there are in the neighboring carbon. But sometimes it becomes a disadvantage when all the hydrogens are coming in the same spot or right next to one another and they're overlapping and the signals, the splitting is overlapping. I can't pick out, it just looks like one big massive multiplet. It's harder to tell what's going on. That can be remedied by using an extremely powerful magnet. So in some research facilities, they have entire rooms that are filled with this massive magnet, and the power of the magnet makes a much bigger energy difference between these protons and these protons. Even though they're both far away from the oxygen, the slight difference in environment can be taken advantage of when I have a really powerful magnet. So that can be fixed, but most academic research labs and labs like ours have a much weaker magnet. So basically we just see this mess because all these hydrogens have really similar environments. Comparatively, the carbon NMR, the peaks don't split. There's no splitting. So each individual carbon, 1, 2, 3, 4, 5, 6, 7, 8 carbons in the structure, each carbon should give a unique, very nice narrow signal. So when you look at your carbon 13 NMR for lab 7, and you look at the scale there, it'll go from probably somewhere around 0 to 220. And we'll talk about where the shift will be based on the environment. But if I have 8 carbons that are all even slightly different, because they're all slightly different distance from the oxygen, I might see some of them pretty close together, but I should see 8 total signals. And most of these, 1, 2, 3, 4, 5, 6, 7, most of these, the first 7 would be quite close together because the first 7 carbons here that are not very close to the oxygen aren't really affected much by it. And then the 8th one, which is right next to the oxygen, would be very distinct from the other 7. Right? So the nice thing about the carbon is every unique carbon gives a signal. I can count them all. I know where their shifts are, and that really helps to, in a situation like this, be able to recognize that the spectrum is a good match for the structure. So here are some examples where there's some symmetry. So if the molecule actually is symmetrical, unlike the last one with the oxygen created a situation where none of those carbons were exactly equivalent. But here I definitely have some symmetry. There's a plane of symmetry here. So the left-hand side and the right-hand side are equivalent. So this carbon is the same as this one's the same as this one, this one's the same as this one, and this one's the same as that one. That's why I get 4 signals. So I have 8 carbons, but due to the symmetry, I see 4 specific signals for those carbons. So you want to definitely make sure that you recognize when there's symmetry. Here's slightly different structure. Instead of the 2 methyl groups being on the 2 adjacent carbons, they're on carbons 1 and 3 of the ring. But I still have symmetry because I can flip it over, or imagine a mirror plane here where one half's the reflection of the other. Rotationally flipping it over like a pancake would also line up this methyl group right on top of the other one. So it's got 2 different types of symmetry. Either way, that symmetry, I can tell that these carbons are equivalent. These 2 are equivalent. This one is unique. These 2 are equivalent, and this one's unique. Right, so it might look like 3 and 5 are similar to you, but they're not. Obviously, 3 is closer to the methyl groups than 5. So that's why I get 5 total signals for that structure. Here, when my methyl groups are on opposite sides of the ring, now I've got 2 planes of symmetry. 2 perpendicular planes of symmetry. So this carbon is the same as this one. This one's the same as this one. And this one is the same as this one. But because there's also symmetry here, this carbon is the same as this one. And this carbon is the same as this one. So really I only get 3 total signals in that structure. So you definitely want to make sure you do enough practice to be able to at least determine how many signals a structure should give. What about this structure down here? So here I have the same degree of symmetry. The top and the bottom are reflecting, and there's also a plane of symmetry here where the right and the left are equivalent reflecting. And if I had any difference, like if I had a methyl group here, that would create a situation where I lose all that symmetry. So I'm looking for groupings of atoms being equivalent on both sides. So this carbon here and this are equivalent. This one is equivalent to this one, and due to the plane of symmetry here, this carbon here is equivalent to that one, and this one equivalent there. So here I would only get 2 total signals. 1 signal in the area where I expect sp2 hybridized carbons to come, and another signal where I expect sp2 hybridized carbons that are directly bonded to an oxygen that's very de-shielding, pulling electron density away. And we'll talk about where we expect those signals to appear in a minute. So the carbon 13 NMR spectrum, as we said, goes from about 0 to 220. And conveniently, it's really cut into 4 sections. And that's based on electronegativity and hybridization of the carbon that's involved. So a standard sp3 hybridized carbon that doesn't have anything electronegative bonded directly to it, so it could be hydrogens, could be carbon. As long as there's no highly electronegative atom here, some combinations of hydrogens and carbons bonded there, I expect to see a signal for that carbon between 0 and 50. If I bond some hydrogens and carbons and at least one more electronegative atom, like a nitrogen or an oxygen, the higher electronegativity de-shields the carbon, just like hydrogens are de-shielded. When carbons are de-shielded, there's less electron density around the nucleus. And so in the magnetic field in the instrument, there's more of an energy difference between the situation where that carbon's nucleus aligns with the external magnetic field versus against. And so I see that appear in a slightly higher energy part of the spectrum, between 50 and 100. Also triple bonds, which aren't really that common, but when you see a carbon that's sp hybridized, that also appears in that area. So that can be a little tricky. We see so many molecules that have oxygen or nitrogen bonded to carbon, and we expect to see peaks there. It's easy to get into the habit of thinking any peak between 50 and 100 is always going to be an sp3 hybridized carbon bonded to a nitrogen or an oxygen or a chlorine or something like that. But if it's a triple bond, it would also be in that area. So you want to look out for that possibility as well. If it's sp2, whether it's an alkene or an aromatic ring, those usually come between 100 and 150. And again, as we said, if the carbon doesn't have any hydrogens, maybe it's all bonded to carbons, that's going to be a smaller signal. Typically, if the carbon is sp2 and it's double bonded with an oxygen, that also is a small signal. Usually that's going to be carbons on either side, so that would also be a weak signal. If the carbon has a hydrogen attached, it might not be so weak. So an aldehyde is usually going to give a slightly stronger signal than a ketone. But those typically occur between 150 and 220. If the CO double bond has either carbons or hydrogens bonded to it, it's usually closer to around 200 on the higher end of that section. If it has the same situation, a carbon or hydrogen bonded on one side of the CO double bond, but on the other side maybe there's an oxygen, surprisingly, that appears on the slightly more upfield section. So if you had asked me to predict, I would have expected the extra oxygen to be more deshielding, exposing the nucleus even more. So a higher energy gap would be necessary, and higher quantities of energy would be down here. But that's not what we see experimentally. So if there's an extra oxygen in there, that's called usually an ester or a carboxylic acid. Those peaks usually are a little bit below 200. So a lot of this is on your formula sheet, so you don't have to memorize too much. But when you're practicing, you definitely want to be working with the formula sheet so you're aware of what is available to you during the exam versus what details you might want to memorize. Alright, so let's see if we can predict the signals here. So first, I probably want to just number the carbons. Actually, before we do that, we want to look for symmetry. Because if two carbons had the same environment, we would give them the same number because they would be equivalent. So is there any symmetry here? Well, it looks like there's kind of some with these two oxygens on both sides. I could maybe imagine a line here, but if I do, clearly this group is not reflected on the other side, so I don't have any symmetry there. And really there's no plane of symmetry or no axis on which the molecule could rotate and remain symmetrical. So I don't have any symmetry here. So every carbon here should give a different signal. Every carbon is at least somewhat different from the neighboring carbons, like this CO double bond carbon looks similar to this because they both have CO double bonds, but this one is in conjugation and is closer to this pi bond over here, and this one's a little bit further away from it. And this one has this extra group attached nearby, and this one doesn't. So they're definitely different. So if I want to predict the number of signals, I expect there to be 9 signals because there are 9 carbons and there's no symmetry. If I want to predict the shifts between 0 and 220, where right around here is probably roughly 100, this would be roughly 50, here it could be 150. So looking at carbon 1, where would it be? Well, it's an sp3 hybridized carbon. It might be a little bit deshielded due to being next to this pi bond. But there's no highly electronegative atom right near it, so I expect that to be somewhere between 0 and 50. And you don't have to know exactly where. The key is to know really which of these sections each peak is going to belong in. So there's carbon 1. Carbon 2 is part of a pi bond. So carbon 2 I'd expect to be between 100 and 150. And I don't necessarily know exactly where. Carbon 3 likewise. Actually, let's make this carbon 3. Carbon 3 and carbon 2 would both be between 100 and 150. They are definitely different though. As long as they're not equivalent, if there's any difference at all between them, they're not going to give the same signal. So I don't expect carbon 2 and carbon 3 to be in the exact same spot, but I do expect them both to be between 100 and 150. And as we said earlier, carbon 2 doesn't have any hydrogens attached, so I would probably expect that one to be a smaller signal, a weaker signal. Carbon 4 isn't directly bonded to a highly electronegative atom, but it's one carbon away from one. So that might be on the upper end of 0 to 50 range. Carbon 4, carbon 5 and 6 are both sp2, so I expect them to be between 100 and 150. Carbon 8 is sp3, and it's not directly bonded to a highly electronegative atom, so I don't expect it between 50 and 100, but it's one away from one on either side, so it's probably going to be pretty close to 50 up in that area. And then carbon 7 and 9 are very similar, and they are directly double bonded to a CO, to an oxygen, and so they'll appear closer to around 200. They're not identical, so they might be right next to one another, but since in the carbon 13 NMR there's no splitting, where there's not going to be any doublets or triplets, and the peaks are quite narrow, they shouldn't be overlapping. So I should be able to see 9 distinct signals, 2 around 200, 4 between 100 and 150, and 3 between 0 and 50. Any questions about that one? On an exam, I might expect you to draw something like this and predict where they are. Like I said, I wouldn't expect you to know exactly where the peaks are, but sometimes you should know where they are relative to other peaks. So for example, we said carbon 8 should be a little bit further downfield than carbon 4, because carbon 8 is closer to more electronegative atoms than 4. So that's really as detailed as we could get with this particular molecule as far as I would expect you to be able to predict. In addition to the carbon 13 in lab 7, you also have been provided DEPT. So if your group has not yet collected all of the NMR data for both unknowns, we should do that as soon as possible this week, so that you can start looking at that data and trying to identify your unknowns from the NMR, mass spec, and IR data. We're not going to get into any real detail about how DEPT spectroscopy is obtained or gathered, but there are 2 key lines in your DEPT that you want to be looking at. The DEPT 90 only shows the CH signal. So on your DEPT that you have from lab, you'll have 3 lines. The top line, you may have some peaks coming up and some peaks coming down. That's your DEPT 35 or 135. The middle line is your DEPT 90. The DEPT 90 only shows CHs, but our machine needs some adjustments, which I haven't had time to make, and personally actually don't know how to make, so I'd have to contact the company. Unfortunately, you may see some peaks on your DEPT 90 that don't correlate with CHs. They may be CH3s or CH2s, so we can't read too much into what we're seeing on our DEPT 90s, but when it's done properly, the DEPT 90 would only show signals for carbons that have exactly 1 hydrogen attached. Any carbon with 0, 2, or 3 hydrogens attached would not appear in the DEPT 90 spectrum. So if I give you an example on an exam, you can assume that the DEPT 90 is properly working and that any signal there is indicating that carbon has only 1 hydrogen. So what we would typically do is we would line up the DEPT, I should mention first, the DEPT 135, it looked like it was working well for y'all. So the top line of your DEPT spectrum you can get into. Any peak there that's pointing up represents either a CH or a CH3. and any peak that's coming down from the baseline represents a CH2. So if I were taking a DEPT 135, for this molecule, and I had that data alongside the standard carbon-13 NMR, that really gives me a lot more detailed analysis of the structure. Right? So here my carbon 1 is a CH3. So that peak will appear in the same position between 0 and 50 on the DEPT. Carbon 2 has no hydrogen. So there wouldn't be a peak in the same spot of the DEPT for carbon 2, because the DEPT 135 only shows CHs and CH3s pointing up and CH2s pointing down. It doesn't show any carbons that don't have hydrogens attached. Actually, let's go in the same order we have here. So carbon 4 right here, it's got one hydrogen, so it would also be a single. So I would see a signal in the DEPT pointing up in at the same shift, at the same ppm value where I saw it in the carbon NMR. I would see it in the DEPT pointing up because it's a CH. Carbon 8 is a CH2. So here I would see the signal on the same ppm, but it would be pointing down. So this confirms that the signals I'm seeing in the carbon NMR, it confirms how many hydrogens each one has, so it makes it easier to confirm whether the NMR matches this structure. Carbon 5 and 6 are both CHs, so they would both give signals pointing up. Carbon 3 and 2. Carbon 3 is a CH2, so that would give a signal pointing down. Carbon 2 doesn't have any hydrogens, I wouldn't see a signal for that. And carbon 7 and 9 both don't have hydrogens, so I wouldn't see signals for those. So what this does is to confirm for me that these two carbons and this carbon have no hydrogens. This carbon had 2 hydrogens, the other ones had 1 hydrogen or 3, but usually if I see a signal between 100 and 150, it's not going to have 3 hydrogens, right? Because this is the area where I see sp2 hybridized carbons. sp2 hybridized carbons never going to have 3 hydrogens because it needs to have a double bond typically if it's sp2. So at most it can usually only have 2 hydrogens, usually 1. But if I see a signal pointing straight up on the DEPT 135, I know it has 1 hydrogen or 3, but as we said, it wouldn't have 3. So I can really, between the two of these, looking at both of them, I can really nail down whether or not the spectra matches the structure, and there'd be very few structures that would match both the carbon and the DEPT spectra that I would see. So this is just the standard C13. The DEPT 90 only shows CHs, and the DEPT 135, my CH3s and CHs both point up, and my CH2 points down. So how would the DEPT potentially be used to differentiate between these two structures? Because if I were just looking at the carbon 13 for one or for the other, what I have here is 1, 2, 3, 4, 5, 6 carbons in one structure, 1, 2, 3, 4, 5, 6 carbons in the other structure. So if I were looking at the standard carbon-13 NMR, I'd see 6 peaks in both, except for the fact that there's some symmetry. All right, so I got to be careful about the symmetry here. In this structure here, 3 and 6 are actually the same. There's a symmetry right here. This bond can rotate, so the OH would be propellering around there, which means 3 and 3 are equivalent, and 4 and 4 are equivalent. So actually this molecule will give me 4 signals, and it would be the same here due to the symmetry here. Carbon 6 is actually equivalent to 2, carbon 5 is actually equivalent to 3, and carbon 4 is unique. So I'd actually have 4 signals in both. One of those signals right here for this carbon and for this carbon would be very similar. they would both be, since they're directly bonded to an oxygen, between 50 and 100. So for both of these molecules, if I were just looking at the carbon NMR, I'd see one signal between 50 and 100. I'd see three other signals for carbons 2, 3, and 4 on both structures between 0 and 50. So it'd be very difficult to distinguish between them. If I did a proton NMR, I could distinguish between them based on their splitting patterns, but with the carbon I can't do that. So that's why the DEPT is so useful when I'm looking at carbon. So if I'm looking at the DEPT, the key thing here would be in this molecule, the carbon that's directly bonded to the oxygen, the one that appears between 50 and 100, is a CH2. So if I were looking at the DEPT 135, this signal wouldn't be coming up, it would be coming down from the baseline. And the second carbon is a CH, so it would be pointing up. The third carbon is a CH2, and so is the fourth. So these two would also be pointing down. So overall there, if I just focus in on the area between 0 and 100, since there's no peaks above 100, I would have a signal above 50 that's going down because it's a CH2, a signal between 0 and 50 that's going up, representing this carbon that has one hydrogen, and then carbons 3 and 4 would both be down since they both are CH2s. On the other side, if I look between 0 and 100 specifically, the carbon that's directly bonded to the oxygen is a CH. So that molecule would give a signal between 50 and 100 that would be pointing up. All the other ones are CH2s, and so they would all be pointing down. So now I can see, even though I have the same number of signals in both, and even though I have one signal between 50 and 100 in both, and three signals between 0 and 50 in both, I don't see the signals pointing in the same direction. And when I look at the DEPT 135, because of the difference in how many hydrogens there are in each carbon in both structures. So even isomers that have very similar structures, if there's any difference, usually that can be distinguished one way or the other in the carbon 13 or in the DEPT. Alright, so here was the first quiz question. If we're asked to determine the number of signals and the shifts, here I have 1, 2, and then due to symmetry 3, 4 signals. Right? We talked about the structure last time. There's a plane of symmetry right down here. Due to the rotation of this single bond, the methyl group would be flipping around, so it would be just as often closer to 3 as it would be closer to 3 on the other side. So if I'm looking at the carbon 13, not necessarily the DEPT initially, where would the signal for carbon 1 appear? Well, it's directly bonded to an oxygen, so I'd expect it between 50 and 100. Carbon 2, also directly bonded to an oxygen, but similar to how we said in the proton NMR, when a carbon has fewer hydrogens and more carbons, it's going to be a little bit further downfield than when it has lots of hydrogens, right? We said in the proton NMR here, we expect these hydrogens to be around 0.9, but then shifted due to their proximity to the oxygen. This one we expect it to be around 1.7, but then shifted due to proximity to the oxygen. So there's a natural difference between methyls and methynes and methylenes. And so in this case, the carbon that's bonded to the oxygen, but has other carbons instead of hydrogens attached, I would expect to see a little bit further downfield compared to the other carbons. So that might be carbon 2. Carbon 3 is one more atom away from the oxygen, and it's still sp3. So if it's not directly bonded to a highly electronegative atom, I expect it to be between 0 and 50. And then carbon 4 is sp2 hybridized, so I expect that to be between 100 and 150. So this would be roughly the expected carbon 13 NMR. And so then if I were to look at the DEPT, we'll just do the DEPT 135. Carbon 3 would appear in the same spot, but since it's a CH2, it's got 2 hydrogens on it, it would give me a signal downward from the baseline. Carbon 1 is also going to be in the same spot. Carbon 1 is a methyl, so that would come up from the baseline. Carbon 2 is a methine, a CH, so it would also come up from the baseline. And then carbon 4 is also a methine, so it would also come up from the baseline. So I can confirm how many carbons are in or how many hydrogens are in each carbon, to some degree at least, and really get spectra that matches this structure and helps to confirm its identity. Just real quick, if I were looking for the DEPT 90, that one only shows CHs. So carbon 3 is a CH2. It wouldn't appear in the DEPT 90. Carbon 1 is a CH3. It wouldn't appear on a proper DEPT 90. Carbon 2 and carbon 4 are both CHs, so I would see a peak in the same spot where carbon 2 should be, and another peak where carbon 4 should be. So the DEPT 90 would only show 2 peaks because there's only 2 different carbons, 2 and 4, that have 1 hydrogen. And in case you're not aware, MRI is a version of NMR. So when MRI was first developed, since it's really no different from NMR, they look at the magnetic. They put you, if you ever have had an MRI, they put you in a big magnet and then they spin the magnet around you. So when we do NMR, we put our samples in a tube and the tube spins. In an MRI, they put you in the tube and they basically spin the tube around you. And the reason it's not called NMR is because when it was developed, people didn't like the word nuclear. It made them feel like they were going to get unsafe radiation. So they changed the name to magnetic resonance imaging instead of nuclear magnetic resonance. And that made people feel better. Obviously, you're only getting hit by radio waves when you go in an MRI machine anyway. And radio waves are the lowest energy form of light radiation. So there's really obviously no danger of going in there. But your body is full of protons. So basically they're doing proton NMR of your body. And the image obviously is very different from the images that we get. We're not going to get into detail about that. I'm not even really personally familiar with it. But you get an image of the tissues based on the concentration of protons or the concentration of water, because obviously water molecules have 2 protons, and that signal that's produced can be used to create an MRI image of your tissues. Would you expect any side effects from exposure to either radio waves or magnetic field? No. Those things are not harmful to biological tissues. The radio waves for sure, the magnetic field also. The only problem there is obviously if you have a pacemaker or something like that that could be affected by a magnetic field, you wouldn't want to go in there because that would obviously be dangerous, but that's not the case for most people for sure. So, any questions about Chapter 16? Alright, so we only have 2 more chapters then to finish out the semester. Chapter 9 about addition reactions. And in Chapter 9, what you'll see is an addition reaction is the opposite of an elimination reaction. In an elimination reaction, we had a leaving group and a beta proton. And we used a base to pick up the beta proton, push electrons in, and kick out the leaving group. And that created an alkene. And we know from our earlier discussions that an alkene is not the most stable molecule. It's relatively stable. There's complete noble gas configurations and no unstable formal charges or anything. But the pi bond, if you recall, is a cloud of electrons that exists above and below the plane of the carbons because it forms when p orbitals on the carbons overlap side by side. So the electron density is mostly here, and it's not that close to the nuclei. So a pi bond, or pi electrons, are somewhat basic / nucleophilic. These pi electrons aren't really that tightly held to the nuclei they're already surrounding, and so they have the possibility or potential energy. They're a little high in potential energy because they have the potential to attract to some other nucleus and form a sigma bond where they would be more effectively shared between atoms. So that's what allows addition reactions to be relatively successful. I've got these pi electrons. I want to add atoms across there and make new sigma bonds. So converting a pi bond into sigma bonds should be something that looks like it would be relatively product favored. And so there are a number of different addition reactions we're going to talk about. We're only going to get through a few of them today. We're going to talk about the mechanisms in detail associated with that. So a lot of addition reactions start with, I'm sorry, I just realized I made a mistake. Oh, never mind, no. These pi electrons are basic or nucleophilic because their electron density can be attracted to either a proton, they can pick up a proton, or they can pick up an electrophile as they act as a nucleophile. So the pi bond itself is an electron-rich area that will attract to something that's positively charged, like a proton or an electrophile. All right, so that's what we're talking about here. When the pi electrons pick up a proton, now they can exist as a sigma bond. So for the pi electrons, that's more stable. The problem is, in the process, it creates an unstable carbocation. So to finish the process off, we might need a nucleophile to come in there and form a bond there so we can make 4 bonded carbons all the way around. It doesn't have to be a proton. It could be an electrophile. It could be some other positively charged atom that can attract those pi electrons in there and form a sigma bond. As we said, the sigma bonds are more stable than the pi bond. So we understand pi bonds are a little reactive due to the fact that they're not strongly attracted to the nuclei they're already surrounding, and that gives them the potential to be a little bit more stable if they form a sigma bond. All right, so this is giving us an idea of what's going to happen mechanistically. Overall, we want to look at both the kinetics and the thermodynamics for any reaction, so to get a balanced view of all aspects of it. So let's talk about thermodynamics. All right, we're talking about equilibrium. That's thermodynamics. That has to do with which side of the equilibrium is favored. Obviously, that's important to us if we want to do a reaction. We want to push it one way or the other and make sure we get as many products of the reaction as possible. And when we're interested in which side the equilibrium favors, we're interested in the value for delta G. So let's do a thermodynamic analysis of this reaction as it's written. So if we want to do a thermodynamic analysis of the addition reaction, these are my reactants and these are my products. And so we want to figure out what's the sign for delta G, and if we want the addition reaction to occur, how can we make delta G as negative as possible? Or if we want the elimination to occur, how can we make delta G as positive as possible? Right? So if we can control the sign for delta G, that will help us control which side this equilibrium favors. Right? That's the nice thing about an equilibrium and a thermodynamic analysis. So let's take a look first. Obviously, the sign for delta G depends on the enthalpy term as well as the entropy term. So let's take a look first at the enthalpy. So just looking at one example, if you want to get a sense for what the actual value is for delta H, if you recall from Gen Chem, we said delta H for a process or a reaction, it can be thought of as the bond dissociation energies of all the reactants minus the bond dissociation energies of all the products, right? Because bond dissociation energy is how much energy I have to put in to break a bond. Right? So to do this reaction in the forward direction as it's shown, I have to break a pi bond, I have to break the sigma bond, and then I get to form two new sigma bonds. So any bond I break requires energy to be absorbed. That's a positive change in potential energy. To break a bond, energy has to be absorbed from the surroundings. But when a bond is formed, energy is released. So that's why we have the negative sign here. We're subtracting the energy that's released, because energy released from the system's point of view is a negative change. And typically, because these pi bonds are more stable, they would require more energy to break if we were breaking them, which means also they release more energy when formed compared to this pi bond especially, right? This is the lowest energy one. It's not a very stable bond. It doesn't take much energy to break it. So if I only have to put a little bit of energy in to break this, but I get to release more energy when it's formed, and I do calculation, I get a negative value. Right? So on an exam, you wouldn't have to go through with all the numbers. You could just say, because a pi bond is not as stable, it starts off relatively high in energy, only a relatively small amount of energy needs to go into breaking it, and that'd be positive. And then when the new sigma bonds form, since they're more stable, a larger quantity of energy is released when they form, and so when more energy is released than is absorbed, I get an overall exothermic process. And that's obviously the exact amount's going to change from one reaction to the next, but that's the general idea and how you could answer a question that asks you about the enthalpy change for an addition reaction. If we were looking at the elimination reaction, it would be the opposite. Right? If we have to break sigma bonds, we have to put more energy in than is released when the new pi bond forms. So that would be a positive delta H in the reverse direction and a negative delta H in the forward direction. All right, so now we have a sense that delta H is negative. Will heat be absorbed by or released into the surroundings? Well, a negative delta H from the point of view of the system means energy is released into surroundings. What will the sign be for the entropy change in the surroundings? Well, if heat is released into the surroundings, there should be a temperature increase in the surroundings. And if the temperature goes up, there's more variety in the surroundings. So the change in entropy should be positive for the surroundings. Right? The reaction releases energy. The surroundings have more kinetic energy. They're moving around more, and that means they're moving around with more variety. Right? We know that at a lower temperature, there's a narrow distribution of different kinetic energies for the particles. When we get to a higher temperature, there's still some moving very slowly, but now there's a lot more moving quickly, so there's a broader distribution of speeds and kinetic energies, which means more variety for the molecules. And so the enthalpy term being negative favors the process, because we know any process that increases entropy for the universe will be a product favored process. It will shift toward the state that produces the greatest total entropy for the universe. And so we have a negative value for delta H here in our term, and that's product favored due to the fact that it increases entropy for the surroundings. So now let's look at the entropy term. So if we want to get the sign for delta G, which relates to the total entropy change for the universe, we need to also look at the entropy change for the system. So what should the entropy change for the system be? Well, we're doing an addition reaction. So we're looking at a situation where we're adding 2 moles of reactants and combining them That's why it's called addition. They're added together to create one bigger product. So in terms of the entropy, there should be more entropy in the system to begin with when the particles are free to move around independently and there's more variety in the ways that they could be positioned and moving in space, versus less entropy in the products when everything's connected and there's only so many ways that one mole of one molecule can move around and be positioned in space, right? So the more independent moles I have, generally the more entropy there is. So without having to do a detailed analysis and quantify the entropy change, we can predict that the entropy change should be negative. The products have less entropy than the reactants, so the entropy is going down. So while delta S is negative, a negative times a negative gives a positive value for the negative T delta S term. So the enthalpy term favors the products. The entropy term being positive overall, once we factor in the negative here and times the negative there, that favors reactants. So usually it's ideal if both of these terms favor the same direction. That way we can really rely on the reaction shifting in the direction they both favor. But it's also kind of an advantage to have one favoring one side and the other favoring the other side, because then we can take advantage of changes in temperature to make delta G either more negative or more positive. So the enthalpy term favors the products. The entropy term favors the reactants. Right? So then the idea here is, since temperature is part of this term, I really can't control the signs for delta S or delta H, but I can control the temperature at which I perform the reaction. I can put it in a hot oil or water bath, or I can put it in an ice bath, and I can really perform this reaction at a variety of temperatures. So in this case, if I want the addition reaction, where I have 2 moles of reactants, so let's say I have an alkene, and let's just say I want to react that with HCl and produce sigma bond from the pi bond. So I've got 2 moles of reactants, 1 mole of products. So if I want to make this reaction shift as much to the products as possible instead of toward the reactants, I need delta G to be as negative as possible. So I want the delta H term, which is negative, to dominate when I add. I want this term that's positive to be as small as possible. So if I lower the temperature down as much as possible, this term will become smaller and smaller and smaller, and the negative delta H will make delta G more and more negative because it won't be offset by any positive, and that will make the equilibrium favor the products as much as possible. So is there any reason why I wouldn't want the temperature to be too low? If I want to favor addition, I want the lowest temperature possible. Is there any limit to how low it can go? Well, from a thermodynamic perspective, just looking at the equilibrium, there's really no limit. I would want this to be as low as I could possibly make it, so this term is as small as possible, and the larger negative value here makes delta G as negative as possible, so it shifts and favors products as much as possible. The problem with that, though, is I haven't factored in kinetics. Kinetically, I can't keep the temperature too low, or the collisions won't have enough energy to reach a transition state and the process will be too slow. So the lower the temperature, the more the equilibrium favors the products, but the lower the temperature, the longer it takes to get to equilibrium. So in a real life scenario, I want to get to equilibrium as quickly as possible, but I also want the equilibrium to favor the products as much as possible. So there's a balancing act there. I need to keep the temperature high enough so it'll reach equilibrium in a reasonable time frame, but I want to keep it low enough that that equilibrium will favor the product side as much as possible. If I want to shift it back in the other direction, if I want instead to favor the reactant side, then as it's written, I would want delta G to be as positive as possible, because a positive delta G means it's more reactant favored. So in that case, I would increase the temperature. By increasing the temperature, I make this term, which is positive, as large as possible. I would need it to be especially large to make it larger than the negative sign here, so that delta G becomes as positive as possible and shifts the equilibrium back. So a higher temperature will always shift the equilibrium toward the side with more entropy, due to the way this equation works out. And so that's an advantage for me. If I want to do the elimination and get the alkene, the side with more entropy, all I have to do is increase the temperature. Increasing the temperature helps it to get to equilibrium faster, and it makes sure that the equilibrium will favor the side with more entropy as much as possible. So that's a nice thing about this. I can make the equilibrium favor whichever side I want depending on how I adjust the temperature. And so that helps with the second quiz question. That's basically what we just said, so I'm not going to go through the exact same discussion again, but just to summarize, the higher temperature favors the side with more entropy. That's the elimination. And the lower temperature favors the side with less entropy, specifically because that side is favored by enthalpy, and that's the addition. So if I want to do an addition, I can't increase the temperature too much, but again, I can't make it too low, or the process won't happen fast enough because the molecules won't collide with enough energy to get to the transition state. So here's an example reaction, adding HBr across a double bond. I'm using a relatively low temperature. That helps shift the equilibrium mostly toward the product side. I get a decent yield. Looks pretty good. So if you have a reaction like this, you also want to be able to predict what the products are going to look like. So that will best be done if we look at the mechanism. So what we said before was the pi electrons are not that stable. They make this grouping of electrons slightly basic. They're going to attract to something that's positive. And when I look at the HBr, the electronegativity difference, clearly I've got a fair amount of positive on this hydrogen. We know HBr is one of our strongest acids. So that's going to force this pi bond for proton. And bromine is going to take those electrons. It's a simple proton transfer. And so when that happens, and the proton adds, doesn't matter which of these carbons picks up the proton and which one forms a carbocation. Right? Because if the pi electrons aren't shared between both carbons anymore, both carbons are not going to have a noble gas configuration if they're only shared between one carbon and this hydrogen, which is what this arrow is showing. So if I put the hydrogen on here, I get this carbocation. If I put the hydrogen on the other side, I get this carbocation. And they're equivalent. There's no difference between the two. One is just a flipped over version of the other. So I don't have to draw both. Just draw one. And then the next step to produce a product would be the Br minus coming in as a nucleophile. It would come into this carbocation. What do we know about carbocations and their geometry? We know that they're flat and they can be attacked by a nucleophile from either the top or the bottom. So really, I don't have this one product. I really have a mixture where some of the molecules have the bromine coming out at me, as well as the enantiomer where some of the bromine atoms will be pointing away. So in this case, it doesn't matter regiochemically whether the hydrogen adds to one side and the bromine the other side, or whether the hydrogen comes over here and the bromine over here. That doesn't matter, because wherever the carbocation forms, I get the same structure. but it does matter which spatial positioning the bromine ends up on, and I would get both of those due to the fact that the carbocation is flat and there's no spatial preference for the bromine to attack from the top or the bottom. So regioselectivity, this molecule is symmetrical right down the middle, so the right and left sides are equivalent. So no, it doesn't matter what side of the double bond the proton adds to. But if I don't have that symmetry, it does matter. So I want to talk about the regioselectivity that occurs when I have an asymmetrical alkene where the two carbons involved in the pi bond are not equivalent due to symmetry. So this is a situation where there's two possible products. I could end up with the hydrogen here and X here, depending on, X could be a halogen or something like that. I could put the hydrogen here and X here, or there's a possibility that the hydrogen could add here and the X could add here. Right? So those are different constitutional isomers. Depending on which atom the hydrogen or the nucleophile goes to which carbon, I get two different constitutional isomers. So a long time ago, this dude named Markovnikov studied this phenomenon, and he recognized a trend, which is now known as Markovnikov's rule. And so what Markovnikov's rule says is when I add HX, like HCl, HBr, across a pi bond that's asymmetrical, that the hydrogen atom will add to the carbon that already has more hydrogen atoms. That's just what he observed experimentally to occur in most situations. And so that's what we see here. This carbon has a hydrogen and a carbon. This carbon has two carbons. So when the hydrogen comes in, it should add to the same carbon that already had more hydrogen. And the nucleophile will add to the other carbon. So he didn't know why that would occur. The mechanism was not understood at all at that time. But that was the observation, and it held true for most molecules. But we want to be able to explain why. So let's take a look at the mechanism, and in addition we'll try to compare how we would have gotten the other product. So the other product would have occurred if the bromine came in here, and it could come in from the front or the back, and the hydrogen would have come in here. Right, so just looking at that, there's really no reason why that would be more or less stable than the other option. So thermodynamically, there's no reason why one of these products would be favored over the other. So there must be a kinetic difference. There must be a reason why the mechanism goes through a pathway that produces this Markovnikov predicted product versus the anti-Markovnikov predicted product, which we don't really see forming. Right? So the mechanism is going to help us understand that, because we want to make sure we can predict the products that are formed in these reactions. It was also observed that if I do the same reaction but I add hydrogen peroxide or some other peroxide where I have carbons on either side of the two oxygens, right? So hydrogen peroxide looks like this. If I put carbon groups here instead of hydrogens, I get a different peroxide. But if a peroxide was added to the reaction, then I get the opposite product from what Markovnikov predicted. This reaction, you'll want to be able to understand enough to the point where you can predict what the products will be. Right? So you should kind of memorize, at least, if the peroxides are present, you get the opposite regiochemical outcome from what you had predicted based on the Markovnikov rule. We're not going to explain this reaction's mechanism until next semester. But we are going to explain this reaction's mechanism without the peroxide. So I would expect you to be able to go through the mechanism when HBr HCl is added to a pi bond, to be able to predict the correct product, and then to recognize that the opposite regiochemical outcome will usually occur if peroxides are used in the reaction. So let's take a look at the mechanism. So the mechanism here is a two-step process. As we showed earlier, the first step is where the pi bond picks up a proton. It's a proton transfer. one of the main 4 patterns we talked about. That produces a carbocation intermediate. Then the second step is nucleophilic attack. The nucleophile comes in and attacks that carbocation to form a new sigma bond there. So on net, we have 2 reactants and 1 product. And so we talked about how the thermodynamics and the entropy difference can be taken advantage of to shift equilibrium one way or the other. But in terms of the mechanism, if we want to predict why the bromine adds to this carbon, well, it's because the carbocation formed there. If the carbocation formed at the other carbon, then the bromine would have attacked there, which would have given the anti-Markovnikov product. Well, hopefully you understand that carbocations on a tertiary carbon are more stable than a secondary, right? So we talked about why that was a while back. We said the extra hyperconjugation and induction here stabilizes this positive charge more than that one. So in this first step where the carbocation forms, which should be the slow step, right? Every mechanism we've seen so far that involved a carbocation, whether it was E1 or SN1, every mechanism that involved a carbocation, the slow step was the step where the carbocation forms. So if the carbocation forms here versus here, well, forming it on a tertiary carbon should be a lot more stable, and it should happen a lot more often there than at the other site. And so since this intermediate won't really form, the bromine doesn't have the option to come in and form the anti-Markovnikov product. This will form through a much lower energy transition state, and so almost every molecule will go through this pathway where the bromine has to come in here and form at the correct Markovnikov predicted position. One way to confirm that this mechanism is correct is to look at the rate law, right? So experimentally you can measure whether the rate is impacted by the molarity of one reactant or both reactants. And so if this mechanism were correct, what would be the expected rate law? Well, if the slow step is the first step, as we expect, since carbocations are really high in energy and they take a lot of energy to form, that should be the slow step to form the carbocation. If that is a slow step, since one molecule of each of these reactants has to collide in that step, both of those reactants should be first order. Right? Adding more of either one of them would facilitate more frequent collisions. The more often they collide, the faster the rate of product production. So if you experimentally run this reaction and measure what happens to the rate when you double either one of these reactant molarities, doubling the initial molarity of either one of these doubles the rate, and that confirms that they're both first order. It doesn't necessarily prove this mechanism, but it does support the mechanism. And there's other evidence. Obviously, the expected and experimentally measured regiochemical outcome also supports the mechanism, forming the carbocation at this position. So the bromine always ends up at that position. Also supports the mechanism as well. Right. So we're pretty confident that this is the correct mechanism due to all the ways that it's supported experimentally. Right. So here's a reaction coordinate energy diagram. We expect the first step to be the slow step because it reaches a higher energy transition state than the second step. What will this transition state look like? Well, when we're drawing transition states, every bond that forms or breaks is represented with a dotted line. Right? So what's happening here is the pi bond picks up a proton, these electrons stay on the bromine. So the pi bond is breaking during this transition state, call that TS1. The pi bond is breaking. This carbon is starting to form a bond to the proton, and the HBr bond is breaking. Electrons are being pulled away from this tertiary carbon to start to form the CH sigma bond. So this carbon starts to take on a positive, right? It's transitioning between zero charge and a +1 charge. So during that transition, it takes on a partial positive. The bromine is transitioning from zero charge to a negative, so it starts to take on a partial negative. So just like many of the reactions we've already talked about, When there are partial charges that form during the transition state, you want to use a polar solvent so the solvent can come in and form attractions to those charges and make it a little bit lower energy, right? If I had a non-polar solvent, the energy of that first step would be much higher, and so the reaction would be much slower. It would happen much less often. Once the carbocation forms, we always want to look for the possibility of rearrangement here. We're not going to see that because it's already as stable as it can be on this particular structure. And then the second transition state here is going to be lower energy. In that transition state, that's when the bromine comes in and attacks. So that transition state 2 is going to be simpler. It's just going to be where the bromine starts to form a new bond to that carbocation. So it's starting to stabilize the carbocation, and by starting to form a sigma bond there. So how would this look if it had gone through the anti-Markovnikov route? Well, if it were anti-Markovnikov, then the hydrogen would have been added to the other carbon. So if we looked at the first transition state there, the hydrogen would have started to add here and would have started to pull electrons away from the secondary carbon. Forming a carbocation on a secondary carbon is less stable once it forms as an intermediate, but it's also less stable to try to form or start to form a partial positive on a secondary carbon versus on a tertiary carbon. So if I went through the other pathway, it would be significantly higher in energy, even though the products would be similar in energy. And so kinetically, it's just not a favored pathway to produce a positive charge in a carbon that can't stabilize it very well. And so that's what we're seeing here. There's two possible products. There's the Markovnikov product that would result from the more stable carbocation, and the anti-Markovnikov product that would form from the less stable carbocation. Which looks more favorable? Obviously, the Markovnikov pathway goes through lower energy transition states and intermediates than the anti-Markovnikov pathway due to the more stable carbocation. Right? The carbocation is more stabilized by hyperconjugation and induction. Make sure you can explain those concepts we already talked about. Maybe review them, ask me about them if you need to, because you might be asked about those again at some point. And so this is just zooming in on that first step of the mechanism, right? That's the slow step. That's the key step. If you want to make the overall process happen more often, we've got to speed up this slow step. We can't have it go through a really high energy transition state, right? So that's what we're seeing here. When the carbocation starts to form on the secondary carbon, it's much higher in energy, just like the secondary carbocation is higher energy than the tertiary one. When it starts to form on the tertiary carbon, it's lower in energy. So that pathway is going to, almost every collision that occurs is going to have the energy necessary to get through that pathway. Very few collisions comparatively would go through the higher energy pathway. So once that slow step occurs, any Br minus around is going to end up colliding here. If this were available, it would end up rearranging quickly anyway for the most part, which would end up giving the tertiary carbocation, and the bromine would end up colliding there anyway. So even if it did go through, once in a while if the collision did go through the higher energy pathway, the rearrangement from the secondary to tertiary carbocation would happen relatively quickly. Then bromine would still attack there, and that would still give the Markovnikov product versus the anti-Markovnikov product. Here's another example. Here we're looking at the stereochemical outcome. Right, so this shouldn't be anything really new or surprising to you. Once the proton is picked up in the slow step, that produces a carbocation. So here, if I'm looking at the mechanism, I want the proton to add to the end so that the carbocation forms in the more stable secondary position versus the less stable primary position. That produces a carbocation. As we know, carbocations are flat. And that flat structure can be approached by the Cl- from the top or from the bottom. If it comes in from the top, it'll be pointing out at me. If it comes in from the bottom, it'll be pointing away. And if the carbon it comes into is a chiral carbon, or a stereogenic center like it is here, that gives me two different stereoisomers. As long as there's only one chiral center in the structure, those two isomers will have opposite configurations, and they'll be enantiomers, which means that I get a racemic mixture of products. All right, so which step determines the stereochemical outcome? Well, that's step 2. Right? Step 1 produces the carbocation. Step 2 is where the nucleophile attacks it, and since it can attack equally from the top or the bottom, I get two equally likely stereochemical products. And then this slide is showing the same thing more generally, just to remind you what the carbocation looks like. All the atoms connected to the carbon are all in the same plane, and the p orbital that's empty is above and below the plane equally, so when the nucleophile attacks, it's just as likely to come in and overlap orbitals here and make the sigma bond as it is to come in at the bottom and overlap there and make the sigma bond there. And as long as the two possible products produced from those different spatial nucleophilic attacks are different, then I will produce a pair of enantiomers. So let's use that information then to look at the third quiz question. Here, I don't expect any of these pi bonds to react with the HBr, and that's because they're in resonance. Obviously, the shifting of the electrons around here means that all 6 pi electrons in the aromatic ring are spread out and attracting to all 6 carbons in a nice molecular orbital covering all 6 of those atoms. So those are much more stable than an alkene pi bond. So I don't expect my aromatic pi electrons to attack the proton in the mechanism we just saw. I expect the alkene pi electrons to attack that proton in the first step of the mechanism. So that would give this intermediate. So would the hydrogen add here or here? Well, this is an example that is an important example, because if I just memorize Markovnikov's rule, I'll get the wrong answer here. And that's the problem with rules versus understanding the mechanism. Right, so when we look at this option, there are really two different pathways this could go through. If the proton gets picked up and added to this carbon here, then the electrons are pulled away from the tertiary side. I get a nice tertiary carbocation. That looks good. If the proton gets picked up here, then I get a secondary carbocation. And that's the reason for Markovnikov's rule. Normally a tertiary carbocation is more stable than a secondary one, but this is an exception because the secondary carbocation is stabilized by resonance and is actually spread out over multiple atoms, whereas the tertiary one here is too far away. It's separated from the other p orbitals from an sp3. It's separated by from them by an sp3 hybridized carbon, and so there's no resonance to stabilize that. So as we've been saying all along throughout the semester, a resonance stabilized carbocation should be more stable than one that's not. So I don't expect a reaction to go through this pathway, and even if it did, I would expect a hydride shift to put the carbocation at the more stable resonance stabilized site. So then the next step would be the Br minus that's created in the first step would come in there and attack that site to make a fourth bond to that carbon. And since it's flat and it's going to become a chiral or a stereogenic center, I expect two products to form. One where the bromine attacks from the front, and one where the bromine attacks from behind. I get a racemic mixture of those two different enantiomers. Questions about that one? All Alright, so let's take a look at this one here. As we said, you want to look out for the possibility of rearrangements anytime you see a carbocation. So here I'm using HCl, it's very similar to HBr. The pi electrons would pick up that proton. The chloride would act as a leaving group or conjugate base of the HCl. When the pi electrons attack, it's going to connect the new hydrogen. This hydrogen here is going to end up here, right? We don't want the hydrogen ending up connecting here because that would pull electrons away and make a primary carbocation, which would be prohibitively unstable. We're not really seeing any reactions where primary carbocations can form even temporarily before rearranging. So try to avoid drawing primary carbocations even as a temporary intermediate. So the proton is going to add to the primary site so that the secondary carbocation forms. Then it's possible for the chloride to come in there, which would produce a racemic mixture where sometimes the chloride would have a solid wedge here and sometimes a dashed wedge. So this little zigzag is indicating that I have both of those outcomes. But since there's a hydride right nearby, intramolecularly, any collision this molecule undergoes that's not a collision with the chloride can provide the energy for this hydrogen to jump over there. And when it does, as this arrow is showing, it would produce a tertiary carbocation that would be more stable, so that would happen relatively quickly. And then the chloride could attack, and I would get this other product. So there's regio issues here, where I expect this to be the major product, and this to be quite minor. But notice what's happening here. The chloride is connected to the hydrogen to begin with. So what that means is, as these pi electrons come out here and start to form a bond to the hydrogen, the chloride is right in the vicinity. I don't have to wait for some other chloride to come in here and collide. It's already right there. So when this carbocation forms, I don't expect as much rearrangement as I normally would for a carbocation, because since the chloride's already in the area, it's already right there and it can collide and produce a significant amount of this minor product. So that is something that you see experimentally. I normally don't see much of this product that occurs before a rearrangement, because the rearrangement being intramolecular normally occurs relatively quickly, because the molecule doesn't have to collide in any specific way. Any collision can provide the energy to do the carbocation rearrangement, so normally happens quite quickly. But since the chloride is already right there after the proton gets picked up, sometimes it will just come into the secondary carbocation before the rearrangement can occur. And if I want to get more of that, I can increase the chloride ion molarity so that there's even more chloride ions all around. And that way, when the proton gets picked up and the carbocation forms there, those chlorides will be more likely to collide, and that would increase the amount of this minor product that I get. So if that's the product I'm looking for, I could potentially get more of it by adding more chloride ions. So that's a phenomenon you want to be aware of as well. All right, let's take a look at this example, see if we can predict the product we would get here. So here I've got a fused ring system. So just to count these carbons so we're all on the same page. 9 carbons. Carbon 1 and 9 are connected. Carbon 7 and 8 are connected. So 7 and 8 are, this connection is closer to you. That's why it's shown on top of the connection between 1 and 9. So I've got my pi bond here. I expect the pi electrons to pick up a proton. These electrons to stay on the chloride. Remember, every proton transfer step needs 2 arrows. So just because you're picking up a proton and that's what you're focused on, it doesn't mean you should ignore the fact that the chloride is pulling these electrons and keeping them. So make sure you show both arrows there. Even if the electrons aren't shown, make sure you show that bond in some way and then show the arrow to indicate those electrons are staying on the chlorine. So after this occurs, I have to decide, is the hydrogen, the proton, going to add to carbon 1 or 2? Well, if it has to carbon 2, then a carbocation forms on 1, and that's tertiary. It's going to be more stable than forming the carbocation at the other position. So I expect carbon 2 to be the position where the hydrogen adds. I expect the carbocation to form. Then the chloride, since I can't rearrange it to make it any more stable than it is, I expect the chloride to come in and either attack from the top or from the bottom. And so that would give two different stereochemical outcomes. So once this ring doesn't have a pi bond anymore, its most stable conformation would be as a chair. So the 6-membered ring I could show as a chair, and then the 5-membered ring I could show like that as an envelope. So the chloride could come in from the top, be here, or the chloride could come in and be over here. So I would get two different products there. And I might get more of one than the other if sterics is an issue. In this case, this should be my major product. The chloride is in an axial position, which causes it to create some repulsion with the other axial groups, but it's just only a single atom. It's not a very big group. When I put this in an axial position, there's more here, and there's this up here, and so that's going to create some steric hindrance with the other axial groups. Not going to be quite as stable. So as the chloride comes in from the top, and it pushes the rest of the structure down, that alleviates some sterics. So that's going to be more often kinetically favored because it goes through a lower energy transition state, and thermodynamically favored because it's being a little more stable in the end, versus having this larger, more sterically hindered stuff up on the top. So you can use the mechanism there to predict the expected products as well. And so then the last type of reaction, addition reaction, so that pretty much covers addition of HBr or HCl across a pi bond. So if you want to add H and a halogen across a pi bond, HCl, HBr are your best ways to go there. If you want to add a water molecule across a pi bond by adding a hydrogen and an OH across that pi bond, then water would be your reactant. Right? I want the components of water to add across there. I need to use water. But I can't just use water because water is relatively stable. And this alkene, even though the pi electrons could be more stable if they were sigma bonded, it's still relatively stable. There's no formal charge or a noble gas configuration that's incomplete. It's really quite stable. So these two, if they were to react, I can imagine what would happen, and I can show that that would go through a pretty high energy transition state and intermediate. Right? So if this pi bond were to pair with this proton and these electrons stay there, what I would get would be the proton there, I would get the carbocation, and when this oxygen takes those electrons, I would get an OH minus. So in the last couple examples, that was okay, because a Cl minus or a Br minus is really quite stable. That's why HCl and HBr are such strong acids. They give up a proton because their conjugate base is so stable. So forming that conjugate base with a negative charge was very easy to do, and then to have it come into the positive also to form that last sigma bond makes sense as well. Here though, OH minus is not nearly as stable. So I don't want to form an OH minus, right? That's why OH is we know from other experiences, is a bad leaving group. In substitution and elimination reactions, to make OH negative, to make an OH as a leaving group, it wouldn't work out very well. So we needed to add a proton to make it a better leaving group. So instead of adding just water, we're going to add the equivalent of H3O+. And that can be formed when water and sulfuric acid are added together. So if you see an alkene and you see H3O+, or the alkene is added to H2O and H2SO4, those basically mean the same thing. The H2O and H2SO4 form, those two combined form H3O+, so you could see it written either way. So So you want to make sure your mind is thinking about a reaction where you're adding H3O plus or water and sulfuric acid as basically being the same thing. So these reactions also give decent yields of the product depending on specific molecules involved. If the reaction occurs over a less substituted alkene, it's going to be very slow. It's going to be 1,000,000 times faster if I have an extra carbon there, and almost 1,000,000,000,000 times faster if I have 2 extra carbons. So why is that? What is that suggesting about the mechanism? Well, that suggests that the first thing that's going to happen, which is the slow step, which is why we have a big difference in the rates, is the formation of a carbocation. So similar to the last reaction, if I use H3O plus, which is also a pretty strong acid, not as strong as HBr HCl, but the positive charge there means the oxygen is pulling these electrons away very strongly. So if the pi bond picks a proton up and these electrons stay here, that produces a water, which is relatively stable. And when the pi bond picks up that proton, it produces a carbocation. So doing that on a primary carbon, if both sides of the double bond are primary carbons, I would have to produce a primary carbocation. Right? If this picks up a proton, it's just, that's it. It's just a primary carbocation. That's really unstable. So that occurs extremely slowly compared to a mechanism where I could form a secondary or a tertiary carbocation. So apparently it's not too slow to measure, which is why we have numbers here. So I guess technically it's possible. You might need a really high temperature to get this to go forward, or really high pressure or molarity, and somehow facilitate these collisions and force them to react, but still going to react very slowly compared to a situation where we form a secondary or tertiary carbocation. So that's an indication that we have a similar mechanism going on. So here's the mechanism. The H3O plus is produced when water picks up a proton from sulfuric acid. The pi bond picks up a proton from the H3O plus, and then water is our best nucleophile around. It's going to come in and attack. Why does the hydrogen add to this carbon and not the other one? Well, that's to produce the more stable carbocation, right? If we picked up the proton and it added to this carbon here, well, then we would have a secondary carbocation, which is not nearly as stable as a tertiary. So that pathway kinetically is not going to be favored. It's going to be much higher in energy during the transition state. So very few of the collisions will go through that pathway. So again, they're same regiochemical considerations we just talked about. If we're forming a carbocation, that's our slow step. We want it to happen in a way that makes it as stable as possible, because that's the step that's slowing everything down, and it should go through the pathway that allows that to happen through the lowest energy transition state. So once this attacks, the oxygen is going to be bonded here. So that's shown here. Now I have my oxygen bonded here. And that has a positive charge, so another water molecule will pick up a proton, and that gives me my product that's stable. So water is not a very good base, but I'm relying on it to pick up a proton. Is it possible that I could add a stronger base to help promote this last step? Is that reasonable? Well, not really, because if I add a stronger base, it'll just pick up one of these protons. Right? If I'm using H3O plus, the strongest base around that I can possibly have is water. Anything stronger than water, like an OH minus or an OR minus, or even like a nitrogen with a lone pair that's neutral, anything that's a stronger base than water is just going to pick up this proton to begin with. So I won't even have H3O plus around. So if I'm using H3O plus, the best base I have is water, which means water has to be the molecule that picks up this proton to stabilize the product. And when it does pick up that proton, it goes from H2O to H3O plus. And that means I'm regenerating, in the end, the same exact catalyst that I used in the beginning. And so that means I don't need a lot of H3O plus, because every time it reacts, it's regenerated at the end. And that regenerated H3O plus that I form at the end here can go back and react again with another alkene and do another reaction. So I can have one molecule of H3O plus react multiple times because it's regenerated after it reacts each time. And that's what allows it to act as a catalyst. So let's take a look at the thermodynamics of this process. So similar to the hydrohalogenation we talked about, which is where you add hydrogen and a halogen across a pi bond. Hydration is where I'm adding water across a pi bond, right? If you're feeling nice and hydrated, you've recently had some water. If you're dehydrated, you've lost water. So a hydration reaction is where water specifically is added across a pi bond, right? So the H3O plus is a catalyst. It's not part of the net reaction, right? It's there in the beginning, and then it's regenerated in the end, so it kind of cancels itself out. This reaction is the exact opposite of an elimination reaction we talked about. We said if we have an OH and we want to do elimination, we have to make it a better leaving group. So we use the H3O plus to protonate this and make it a water, and then when it leaves to produce a carbocation, there's a beta proton here, and so then a water molecule can pick off this beta proton and push those electrons in, right? So this would have already left, creating a carbocation. The beta proton gets picked off, electrons swing in, that gives me the alkene. Right? This is a reaction we already learned, but we learned it in Chapter 8 when we were talking about elimination reactions. When we learned that reaction, we said it can go both ways. So now we have the ability to look at the mechanism from in both directions, and we can also look at the thermodynamics here and make sure we understand how to shift the equilibrium. So we already talked earlier about how the entropy term here favors the elimination side. Right? There's more entropy when I've got 2 moles of particles moving around with greater variety, and less entropy when I've got everything connected together in one molecule. So the entropy here favors the elimination. And if I want to shift the equilibrium to that side, I increase the temperature. Increase in temperature always makes delta G more favoring the side with more entropy. But we also said at the beginning today, we confirmed that the pi bond is not quite as stable as a sigma bond. So I also have to break a sigma bond in the water, and I break a pi bond, but then I get to form 2 new sigma bonds. So since the sigma bonds are more stable than the pi bonds, the enthalpy term favors the products. And so if I decrease the temperature to make the entropy term as small as possible, then the enthalpy term, which is going to be negative, is going to favor the product because that'll make delta G more negative, favoring the products. So again, I can use temperature to control which side the equilibrium favors in the same way we discussed earlier today. I can also use Le Chatelier's principle. Because water is a reactant, if I increase the amount of water, which means I'm diluting the sulfuric acid, that should shift the equilibrium toward the product side. So adding more reactant shifts it to the product side. And since water is cheap and accessible, obviously, I can really add a lot of it and without much expense, and I can really help to shift that equilibrium toward the side I want. And that's why when we talked about elimination of an alcohol to make an alkene in Chapter 8, we said we use concentrated sulfuric acid to do that. Because we don't want a bunch of extra water that's going to shift the equilibrium back toward the side where the alcohol compound is located. So concentrated sulfuric acid with very little water shifts the reaction toward the other side. And that leads us to the final quiz question, which was about the concentration of the acid. Right, so we just talked about that. If I'm talking about an acid-catalyzed hydration, specifically, This is the reaction, the hydration. We're adding water across a double bond to make an alcohol. That's what a hydration is. So if I want to facilitate the hydration, I need more dilute sulfuric acid. So how and why does the concentration of an acid affect whether the hydration favors the products versus the reactants? That's exactly what we just talked about. I want diluted acid because when I dilute the acid, that means I'm adding more water. And since water is a reactant, it shifts the reaction toward the other side by Le Chatelier's principle. If I wanted it to favor the other side, I would put less water in. So it's not necessarily about adding more moles of catalyst, to just make that clear. So adding more moles of catalyst would not affect the equilibrium. Because a catalyst is not a reactant, nor is it a product. Adding more of the catalyst is not going to shift it either way based on Le Chatelier's principle. It will help me get to equilibrium sooner, but it won't shift equilibrium and produce more products or more reactants once the equilibrium is formed. So we're not talking about adding more or less catalyst here. We're talking about adding more water to dilute the catalyst, because water is a reactant in the hydration reaction, and adding a reactant in the hydration reaction will shift it toward products in the equilibrium. Any questions about that one? And we have similar regio and stereochemical concerns here when it comes to hydration, just like with hydrohalogenation. So if we want to understand the stereochemical outcome, we want to look at the mechanism. As we said, it's almost the same exact mechanism, except instead of the pi electrons picking up a proton from HBr HCl, they're going to pick up a proton from H3O+. And I need to show my other reactant, obviously. There's a water there. But the pi electrons pick up a proton from H3O+, and that's going to produce a carbocation. So what we've been saying is regiochemically, the carbocation should form on whichever carbon can stabilize it better, which is the tertiary one. And that means the hydrogen is going to be picked up and connected to the other one, right? So there's already one hydrogen here. Now there are two. Once the carbocation forms, the water molecule is going to attack. And that is the step where the stereochemical outcome is determined, right? Because as we've been saying, the carbocation is flat. The water could come in from the top and end up with the solid wedge, or it could come in from behind and end up with the dash wedge. And then the last step would be the deprotonation, or the removal of that other proton from the water to leave me with an OH. Right? So the reason I get a 50-50 mixture of these products is because there's a 50-50 shot in terms of whether the water comes in from the front or from behind the carbocation. And since it's producing a carbocenter, these two molecules are not identical. Despite being mirror images, they're not superimposable, so they are different, and you would need to draw both structures for full credit in that situation. Again, if you wanted to draw both structures without having to draw both, you could do this, where you show this type of zigzag. That implies half the molecules have a solid wedge for the methyl and a dash wedge for the OH, and the other half have a solid wedge for the OH and a dash wedge for the methyl. So this, drawing it like this is the same as drawing it like this. Hydration is a common way in industry of producing ethanol. So typically the ethanol you consume in an alcoholic beverage is produced through fermentation, especially if you're drinking beer. Even if you're drinking liquor, usually a fermentation produces the alcohol, and then a fractional distillation is used to get the alcohol more concentrated. But in industry, where we're not with contaminants that might be poisonous because we're not drinking the alcohol, it's common to convert ethylene into ethanol using H3O+. To do this, though, you need some pretty harsh conditions because, as we said, that would go through a primary carbocation intermediate, which is really unstable. So we wouldn't generally do that reaction in the lab. They might only do it on a large scale in the industry to take advantage of the fact that they have big, massive reaction vessels that can hold things that are extremely unstable and reactive and under high pressures and temperatures to get the collisions they need to occur. So let's take a look at this reaction though. So this is a question that you might be presented with. So here I understand that the H3O plus is my catalyst, so it's going to get involved in the beginning. It's going to then be regenerated in the end. The pi electrons are going to pick up that proton. These will stay behind. And I'm going to get the carbocation here where it's more stable. So that would be my intermediate. Once the carbocation is formed, the water can attack. So in this situation, it's a little bit different from what we just talked about. It's true that the carbocation is still flat, so there's still space for the water to come in either from the front or from the back. But I do have another chiral center already in my structure right here. This chiral center now is creating a situation where the methyl group is pointing out at me. So the front side of the molecule that's closer to me is a little bit blocked more by the methyl group, and the back side is not so blocked. So if I don't have any chiral centers in my intermediate, there's no way to control which side the water attacks from. But if there is a chiral center, that creates a situation where there now is a spatial difference between the water coming in from the front versus the back, and those, if one has more steric hindrance than the other, it won't happen as often due to that transition state being higher in energy. So in this case, with the methyl group kind of blocking the front, not entirely, I would still expect to get both products, but maybe not a 50-50 mixture. So I would expect most of the time the water would come in from behind, and the major product would result from that. And so the major product would have the water molecule with a dashed wedge, and that would push the methyl group out at me. And then another water would pick off a proton there and regenerate the catalyst. And that would give me this product here. As my major product. The same reaction sequence would occur. Sometimes the water molecule would come from the top, even though it's blocked. It's not blocked majorly by something really massive, and a carbocation is usually pretty flat and open, so probably I would expect it to come in there as well, and it would go through the same mechanism and eventually produce the other product, which would be more likely to be minor because the OH would be blocked to some degree from coming in on the same side as that methyl group. Right, this methyl group right here is no impact on which side the OH, which side the water comes in on, because it's in the plane. But this methyl group is spatially positioned with a solid wedge, as we see here. Initially, it's definitely a solid wedge. So that's why this structure would be a little bit more minor for the OH to come in on the same side as that methyl group's already kind of blocking slightly. So be aware of that type of situation as well. Any questions about today's material? There's a lot of bullet points and plenty for you to practice related to both the carbon NMR and addition reactions. As always, the material we covered today won't appear on your exams until next week. On Thursday, we're going to talk about more addition reactions. So a couple of these reactions, the mechanisms will be a little more too complex for us to get into detail on. But we're going to talk about 1, 2, 3, 4, 5 different addition reactions. So if you want to be well prepared to discuss all the different details associated with those, it would be helpful to watch these videos and read that section so that you'll be prepared for that, and also obviously to help you answer the quiz questions that are due before a lecture on Thursday. All right. Please feel free to message or speak up if you do have any questions. All right, everyone's gone. Bye, everybody.